Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 68, and this question asks us to explain why an optically active solution of this r-alpha-methylbutyrophenone loses its active properties, its optical properties when dilute acid is added to solution. So let's use this as a starting material and see what happens when we add a solution of dilute acid. So if we draw our starting material, and we say dilute acid, so that is any HA, any strong acid in water. So remember, HA is any strong acid, so HCl, H2SO4, any strong acid, and it's in water. So when it's in water, your strong acid will dissociate to H plus and A minus. So the first thing in this question is let's do the mechanism or reaction when you add dilute acid. So let's identify the nucleophile and electrophile. So nucleophiles here, well, we have a very electron-rich benzene ring, and we have a very electron-rich oxygen with lone pairs electrons. So this can act as a nucleophile, and obviously your proton of your acid can act as an electrophile. So your carbonyl oxygen will make a bond with the proton. Now you have oxygen with 3 bonds, and that gives it a formal positive charge. Remember, oxygen doesn't like having positive charges. It likes being neutral or negatively charged. So now we want to neutralize oxygen, and we need to reform our acid catalyst. So we right now used an H, and that gave us A minus because the bond between A minus and H broke to give us A minus. So we need to reform our HA. So how do we reform our HA? Well, we can pick up the proton alpha to this carbonyl. So if we use A as a nucleophile now, making a new bond with this hydrogen, when you make a bond, you break a bond to form a new pi bond. When you make a bond, you break a bond, and this will do 2 things. Number 1, it'll reform your acid catalyst. Number 2, it'll neutralize your oxygen, making sure it only has 2 bonds. But now a consequence of this is that from a chiral molecule, you went to an achiral molecule. So if you see here in the starting material, this carbon had 4 unique substituents. It had a methyl, a proton, an ethyl, and this group here. So you had 4 unique substituents around this carbon, making sure, or therefore defining it as a chiral carbon. So chiral carbons with 4 unique substituents are optically active. If you were to shine plain polarized light around this chiral carbon, it will rotate light to some degree in a specific direction that is experimentally determined. But optical activity only exists for chiral centers. Non-chiral centers, such as this carbon, because this carbon has 2 bonds, which is bounded to the same substituent oxygen. So this does not have 4 unique substituents. Neither does this carbon. This carbon has 2 protons, 2 hydrogens bound to it, so it does not have 4 unique substituents, so these are achiral carbons. The only chiral center in this molecule was this one here. But when you add dilute acid, we actually lose chirality around this carbon because we gain 2 bonds to this carbon. So we actually lose 4 unique substituents. We have a methyl, an ethyl, and 2 bonds to this carbon here. So we actually lose chirality in our product, and we form an achiral product. Therefore, achiral products are not optically active. Optical activity is only around chiral centers. Because we do not have any chiral centers in a product, our product is not optically active.